Welcome to another episode of the Distributed Data Show, brought to you by DataStax Academy, where we bring you the latest news and interview technical experts to help you succeed at building large-scale distributed systems. Welcome everyone to the Distributed Data Show, live in the studio in San Francisco. Today with me is Dwi Hai Dong. Hi.
Hello, Patrick.
How are you today?
I'm fine.
So we have an exciting guest today, remote, joining us from way east, South Carolina. Wow, that's a far away. Dr. Denise Gosnell, and that's how I pronounce her name, is Gosnell. I know there's multiple pronunciations, but we're really excited to have you. She just joined DataStax recently. Super excited to get her on the show to talk about graph data. And welcome to the show, Denise.
Yeah, thank you. I'm really excited to be here. Looking forward to this discussion, whatever ends up coming about it.
It will go in random directions, I'm positive, because I got you two on here. So that's just a preview. If you're, it will happen. So Denise, before we get too crazy, why don't we level set? Who are you and why are you here? Tell us about yourself.
So my first history started with a degree in mathematics, and then after that I went to grad school. And truth be told, I was sitting there trying to register for classes for my master's in math, my first semester, and I got locked out of all the required classes, and there's literally nothing left except for this one class called graph theory. So I signed up. It was the only thing available, plus some other kind of elective. I go in there on the first day class expecting a whole semester of discussion about pie charts and like bar charts and the theory of maybe like data visualization or something like that. And well, lo and behold, graph theory has nothing to do with that, and it has everything to do with modeling data with relationships and vertices and things like that. So that's how I stumbled into this, and it opened up my world to something I'm extremely passionate about and that I can talk about forever. So after that, I continued on to get my PhD in computer science, because at the University of Tennessee, graph theory was within that department. And afterwards, I went to a startup to build the health graph for the healthcare industry. And that's kind of how I stumbled upon this group, because I was using Titan at the time, spent about 1.5 years architecting and querying and really enjoying that project. And afterwards, I found that working here at DataStax was a natural fit to bring together my love for graphs and helping people be successful with building their own graph.
Wow, that's quite a story. And yeah, it's funny because you mentioned that about graph. If I wear a shirt with the word graph on it, everybody thinks just that. Oh, it's like pie charts and stuff. No, it's not. Yeah. And then, Mom, I don't want to explain it to you. The reality is that we have a big education to do for the rest of the world. But then again, they don't know about relational databases either, do they?
No, and then that's even better when you're trying to describe the relationships of a graph versus a relational database, and those two words, things get mixed.
Well, we are really excited to have you at DataStax, because we like to think we collect all the smart people, and here you are. So you just up the IQ in the call. So you're going to be doing this talk at Graph Day, and if anyone else doesn't know that, you should know this. Graph Day in Seattle, and you and I have talked about this quite a bit. I think it's going to be a pretty dynamic talk, for lack of a better word. The thing that we talked about, which I think is so important, and this is probably a bigger problem in the graph database world anyway. You've seen this before. Everybody that's new to graph comes and shows up, gets super excited, a little over exuberant. Everything is a graph problem, right? So it's all graph, right? Your rebuttal.
Yeah. So that's the theme of my talk coming up here in Graph Day Seattle, I think October 20th, 21st, sometime around then. But essentially my view of this space from a data science and a data modeler architect perspective is inherently not everything is a graph problem. And as I see it, and we'll kind of get into this, but I see 3 buckets. I see those problems that people are misclassifying as graph problems, and they're really not graph problems, and they're over here. And then of the world of graph problems, there's a lot of really interesting things to get in there, but I see that space kind of divided into 2 sections. You've got problems that are more like a graph database problem, and then just a graph modeling, a cool analytical approach to come up with a creative solution. So those are the 3 buckets. That's the way I see this world. The things that are not, And then within the things that are, you have the database problems and then just the cool analytics problems. And so I'll kind of be getting into that and talking about some of the issues that arise when you make assumptions with your architecture when you might not be going down the right path to begin with.
So Denise, tell us, if you choose the bad problem and you decide to apply the graph data model on a problem which is not a good fit, what are the downsides?
Yeah, so the immediate downsides you're going to have are very similar to trying to fit a square peg in a round hole. What you're going to run into is a massive issue with expectations and performance. There's going to be so many different ways you can attempt to model that graph problem. There's going to exist a way to query it with Gremlin to get that answer. Mm-hmm. But at the end of the day, the way that your performance is going to end up happening, you're going to have a bunch of under the hood, OLAP, entire global graph scans, and you're really not going to be able to get much out of answering that question because it's just not going to be performant or even return from an SLA perspective. So to really drill in and just say, what's the downside? It's going to be expectations of performance. And in addition to really causing a massive problem with, at the onset, developer confusion around, well, how could you model this problem? Because there's going to be so much flexibility on how to squish it into a graph.
Yeah, but when you say that about performance expectation, isn't it related to the implementation of the graph on the database? Suppose I will give you a counter example. Suppose your graph is so small, right? You have a graph, okay, but it's so small, like 200 megabytes of data. It can fit entirely in RAM. In this case, is performance the real issue, or isn't there another issues?
Well, so it also kind of depends with this problem. So I kind of set this up by saying there's 3 buckets. And this example you're bringing to me at this time, I would kind of put that in the middle classification of, sure, it's a graph problem. You've modeled it with a graph. It's going to fit in memory. It's got some cool analytical application. Mm-hmm. It might take a little bit for you to run your algorithm across the graph and for you to come up with a cool answer for whichever problem you were solving. Mm-hmm. So there's going to be gray area. There's a little bit of a flow between one of these and the other, and there's not some perfect answer. But to me, what you're describing is a cool graph application that you can fit in memory. Mm-hmm. It can fit on one machine. There's no need to have a discussion for a globally distributed database. That's a completely separate problem.
Okay.
And all of these questions you can do in memory, go ahead. I mean, have fun. There's some really cool problems you can solve.
Oh, okay.
Well, how many times have we had this discussion in any data problem where you have, hey, I'm going to use Spark and it's a single file?
Yeah.
Are you just trying to show off that you can now use Spark here? Because that's not the problem anymore. It's not, if you have a petabyte data to sort, Spark's great. If you have a 200 meg file, use grep.
Yeah.
It's a different. I think it is a problem it's across every single field, right? Every single topic. Exuberance.
We've all got multiple tools, and our tools that we have can solve multiple problems. And you can also just bring in the hammer and just slam it, and you're going to solve a bunch of stuff. It just might not be necessary. Yeah. That's where you're going to see a lot across these 3 buckets that I'm kind of having my theme. There's going to be some ebb and flow, and you can make it work in one to the other, but at the end of the day, it really just depends on what you're trying to build, mm-hmm. what you really care about, what questions you're really trying to answer, and at the core of it, what engineering problem you're really trying to solve.
So we talk about bad fits. Can you give us a typical example of a good fit for a graph database? A very typical example.
So I don't know if you mean typical by, I want you to tell me an exact problem, but what I am going to say is, if your data and extracting useful information out of your data inherently relies on modeling relationships from one piece of your data to the other piece of data or some other data, as soon as you see that as your fundamental engineering problem, that is when you want to start stepping into the world of graphs. Mm-hmm. If you are looking at your data and looking at your problem and you want to start to understand the distribution of, say, a few properties and maybe how a sliding scale on changing the value affects another distribution. We're starting to talk about global properties and how they're allocated across your data, and that is not a graph problem. That's trying to just understand fundamental properties about the data you have and how that may affect its own distribution within that data set. But that's way different than if you have a user and that user has a relationship with something else in your data set, another user, or content or a product. That relationship is what you want to model with a graph.
Okay, so I want to challenge you a little bit. You said whenever the value of your data is in their relationship, so it may be a good fit for a graph data model. But if I think back, relational database, we have the term relation, right? In the classical relational database, we have relationships by definition. So isn't it also a good fit for this kind of problem?
Are you defining the good fit just by the use of the root word relation?
Yeah, so what I mean is, what differs graph data modeling from relational database models? Because in relational database, you can also model relationship, basically.
Yeah, you can. And the way I do see it, again, it depends on what you're trying to get back out of your data once you've put it into either of these models. And when you want to get back out an understanding of that pie graph that kind of is from the beginning, if you want a pie graph of a distributed key and its values throughout your set, relational database model, that's going to be optimized for being able to grab and extract those insights on a little bit, right? There's a little hand waving happening there. But it's going to be able to be semi-performant on answering those questions. But that's very different than if you want to be able to very granularly describe just the relationships between one entity and another entity in your data. That has nothing to do with the values that entity relates, or the values that entity encompasses from different types of keys and values within that entity. It's all about taking that entity and looking at its edge to something else, or its relationship to other items in your data. In my head, that's completely separate, and there really is a definitive line. I don't know if I've done the best at articulating that for you, though.
It's pretty clear for me. So now tell us, what are the fundamental biggest challenges in graph problems, like the issue that you face all the time on any data model?
So I can go in two directions with that. I can go at it from a use case perspective on where people always start and the fundamental problems they have when they're starting. Or I can kind of go with what are some of the really difficult engineering problems we're having from a database perspective. I'll give a high level on both, and just let me know.
We can dig in after that.
And then follow the rabbit.
We're kind of go with it. So from my experience, like I mentioned previously, I got started off into the specific graph database world, wanting to look at the relationships across healthcare data. And just like many people, when they start, they see the power of graphs, they understand and they're hearing that the real value here is having an entity and getting it in that graph database or in that graph model and being able to model its relationship to another entity. The inherent problem that they're forgetting and that you're not taking into account so that you can get there is being able to deduce or be able to resolve all of the versions of that entity that you have across all of your data. You could have a web app, and you could have all these different instances of users of one individual user that you have. And essentially every record of that user is an immutable entity. It's a thing. This person existed, and here's their data. You can't erase the fact that that user was there. But being able to look across all of your user data and resolve that, these 6 instances of immutable data represent the same person. These over here, they're the same person, and this one guy's all by himself. That step of entity resolution needs to happen so that you can get the power of modeling a single entity and its relationship to another single entity. I think that's a problem that people skip over when they initially start looking at graph databases. They'll slam some vertices and some edges in their graph, and they start modeling, they get it up in prod, and they're inserting stuff, and life is peachy. But then you might want to merge with another graph, or you have another set of data that you need to get into this graph model, and that's where things start getting really hairy. being able to, deduce which vertices are the same or which entities represent the same thing. That's difficult.
Okay, so basically, yeah, it's all about data cleaning and data classification before injecting them in the graph model, right?
I don't want to make that strong an assertion because I also have found that there are some problems where graph models for doing identity deduping is a very successful application. Okay. What I'm saying is that you need to consider the type of entity resolution you need to do up front in order to understand this is my one person that I care about. There are some graph models or there are some graphical approaches in which the relationships between entities do kind of find that social fingerprint for you that gets you that person you're looking for. Or there's a lot of more legacy systems around being curious about, fat fingering last names into a database from 10 years ago, and you just need to know how close this name matches someone else's name. So I'm not going to go ahead and I'm not going to say that, entity resolution, put it outside of a graph, because even within that space, I see two different worlds of problems. Some are great for graphs, some are not.
Well, you have the OLAP versus OLTP as well. I mean, and I think that's the clear definition that we need to make, is that OLTP workloads should be just that. Do not think you can get a faster OLAP to be OLTP.
Exactly. And so when you first asked this question, we kind of went down a hole on the problems I see that people have when they start setting up their use cases. And I mentioned that there's two ways I can go. And you've got the engineering problems. And I think that kind of brings up what you're mentioning, Patrick, around OLAP versus OLTP. There's a really interesting problem right now that has a lot of great minds thinking about it. There's some research out there. And that problem is around when you're looking at the perspective of, all right, I've got a globally distributed graph. My vertices and my edges are existing on servers all over the world in different partitions of Cassandra. There's a very interesting graph problem that comes out of, well, how do you best partition your vertices so that when you're traversing your edges, you're minimizing the number of servers that you're hopping to then give you OLTP performance? Because if you're traversing down a path of length 6, unless you have those vertices properly set up in a Cassandra partition, you could be hopping all over a bunch of different servers, and then your SLAs are going to, essentially blow up a little bit. That problem of being able to cluster vertices inside certain groupings that are optimal to minimize that crossover between edges, that graph partitioning problem from a theoretical perspective is an NP-complete problem. And yet we've got databases out there that need to know this today. And so that's a very interesting thing. I know that the engineers and all of the graph team here at DataStax is working on. It's really great to get to be a part of that and listen to those conversations.
Well, I think the solution, as everything that is NP complete, is quantum computing. That'll fix it, right?
Yeah, well, if that happens, then the entire internet is insecure, so we've got other problems.
But I get an OLTP workload on my graph, so I think I'm pretty happy with that.
Okay, good.
Yeah, no, that's great.
Meanwhile, your financial data is everywhere.
Yeah, that might be the downside. Well, I mean, I think you bring out a really good point, though. There is, to quote, no magic that is really about knowing your data. There's still not a place where you just dump data in and hope for the best. There's a certain amount of knowledge you need to have about what you're doing.
Nor is there one tool that if you put your data in that tool, it's going to solve all your problems.
Right, and that does seem to be. I see a lot of people looking for that lost city of gold that just doesn't exist. Where's El Dorado? Doesn't exist. And
I'm going to hang out here on the beach in Charleston while you guys all look for that.
Yeah,
it's a way better time.
You're going to die in the jungle. But it is, and I think it's a great, it's a great nirvana to think about. Maybe it exists, but we just need to be honest as computer scientists that this is not something that exists. That we have a duty. This is why we get paid to use intelligence when we pick data models, and the data model is not optional, and the tools that we use are not optional, nor are they forgiving. They're not going to give in to our will because we want that. I'm not a 3-year-old. It will work the way it's supposed to work. Understand how it works, understand how to data model with it, your life will be a lot easier, and you'll probably be gainfully employed.
Yeah.
Yep.
I was thinking about one specific big challenge in the graph, which is the supernode challenge, right? And because as a data modeler, I'm helping customers every day, and I can see this pattern coming again and again. Not necessarily only graph problem, but also data modeling in Cassandra problem. Let's say you have a general data set, and 1% or less than 1% of your data, we call this the outlier data. They have huge cardinalities, but only 1%, right? 99 other of your data is perfectly fine, they have small cardinality. And the challenge for me as a data modeler is, okay, should I accommodate all of my data model just to solve this 1% scenario of my data set? Because everything is trade-off. So if I accommodate my data model to fit those 1% of my data set, it means that it adds extra constraint on my other 99%. And so this is my problem. Can I find a happy medium between, okay, solving this 1% and making the other 99% happier?
Whew, it's talking about NP complete.
Not
you got an answer for that one, Denise?
We can see it from the theory perspective,
right?
Or we can see it from the engineering perspective.
Yeah, and I think this might be one of those topics that, as I get my DataStax feet under me a little bit more, it might be a good topic to kind of come back to, because right now I kind of have this potentially too naive answer or look on that problem. So who knows? But the way I kind of see it at this stage is that when you do have your supernode problem, it comes down to avoiding traversals, or at least that's what I want to keep myself from doing, traversing through that supernode, because that's when you get, no matter talking about OLTP in a graph database or OLAP just for solving fun problems, when you traverse through it, that's when it becomes a problem. So from my naive perspective, I would look at that and I would say, all right, well, why don't we make that a property? That would give us the ability to lasso vertices with that property if we want. But then from an OLTP's perspective, we're obviously going to be starting with a very large number of vertices, very large being pretty hand wavy, but you're going to be starting a traversal from a very large number of vertices, and that's already going to get you started on the wrong foot. So I would look at, wanting to start from a different subset of properties, maybe looking at how that property that is shared among those 1% in combination with another property starts to make it a little bit more granular.
So divide and conquer.
So this
maybe
this is setting up an awesome cliffhanger. And Denise, this is great because I think this ends things really nicely. Is the answer is I'm not really sure yet means that I would love to have you come back and tell us more.
Yeah.
So
about all right. Well, now that's putting us in a specific direction.
Well, it is. Well, or you said there's some things in my journey that I'm learning that would be helpful for others, but currently underway, and we would love for you to come back if you could come back.
I would love to. I'm really looking forward to, especially knowing I'm not even a full month in. We're still looking at weeks of how long I've been here.
Well, we count hours, but sure.
Just to kind of capture the degree of the different types of knowledge buckets that I gained and other types of experience. So I'd love to.
Yeah, that sounds great. I mean, because I really pointed out something is that there's some domain knowledge and things that are really interesting, but are they solving the problem? Or are they not? How do you solve it? Using DataStax products, there's a lot to choose from. I mean, there's a lot of things you can do with it. Is it the right choice? And I think that'll be really interesting. Especially with good, smart people talking about topics that are truthy. We love the truthiness. So I think that we're going to
glad that you guys think I bring truthiness to this show.
So far, until somebody puts in the comments, Denise is not truthy.
Okay, well, I'm sure we'll have that.
I really doubt it. But we do invite people to, if you have a comment, bring it to the YouTube channel or meet us on Slack. You're on our DataStax Academy Slack, I'm sure. If not, we'll fix that.
I'm there.
We have the DSE Graph Slack channel in DataStax Academy Slack. That is a great place to interact with the people at DataStax doing graph all day, eating it for breakfast. It's on the spit roast for lunch. It's all there. Having it with a side of Cassandra, and happens every day here. Yeah. I like to throw in a barbecue reference. All right. Well, thank you very much for joining us today.
Thank you.
Thank you, Patrick. This was awesome.
And thank you, everyone, for joining us on the Distributed Data Show, and we will see you next time. Thank you for joining us again for the Distributed Data Show. We love your feedback, so go to the Distributed Data Show page on DataStax Academy and tell us what you think. You can also find us on the DataStax Academy YouTube channel, or find our podcast on iTunes, Google Play, or wherever you get great podcasts. While you're there, make sure and subscribe so you don't miss a single episode.